Hello, class. As our last topic for graph theory, we're going to talk about something called Alerian Trails and circuits, and then later we'll talk about something called Hamiltonian paths and cycles, and then we'll talk about some applications of these two topics. So let's start with the idea of an Eulerian trail. So the motivational question for this involves this map of the city of Königsberg. Suppose I start somewhere in Königsberg. You can start anywhere on this picture you want. And my question is it possible for me to walk in a path where I cross each bridge exactly once? And so perhaps I start on the South Island, then proceed up to the Middle Island, and then the top, and then maybe through doing that I cross Bridge 5, and then Bridge 1, and then I come back down across Bridge 2, and then across Bridge 6, and then up 7, and up 4, but I didn't quite get there because I missed Bridge 3, and so you can try a bunch of variations and see if you can come up with a solution. But not so secretly, I can interpret this question as a graph theory question by redrawing a graph that I can associate to this picture. Namely, I'm going to put a vertex at each landmass. So there is a southern vertex, a northern vertex, then there's the middle one, and then there's the far one over here. Okay, so this corresponds to the southern landmass, and so then this is connected. So this is the middle one. It's connected to the one over here. This is connected to the one over here. This is connected to the one over here. Let's see, and then there's these bridges and these bridges. Okay, and so I get this. And so I can reframe this question that I was originally given as, is it possible to have a trail, remember a trail is just a walk that doesn't repeat edges, through this graph that hits every edge exactly once. And so you can, again, sort of try and imagine, like, I'll start here and go there, and then there, and then there, and there, and there, and there, but then I missed that one. You can try a bunch of different ways and see if you can make it happen. Now, the astute among you might note something, which is maybe rather important to acknowledge, which is that this thing isn't a graph by our definition of graph. Why? Because there's actually duplicate edges between these two vertices and also between these two vertices, corresponding to the fact that there are actually two bridges between the South Island and the West Island. There are duplicate edges. Now, for purposes of what we're going to talk about, that's actually not going to matter in anything we talk about. So throughout this section, we're going to somewhat relax our sense of what exactly it takes for something to be a graph. And so we're going to allow these kinds of duplicate edges, and it's not going to change anything. But just be careful whenever you're thinking about graphs that there's potentially a lot of different things that you might or might not allow depending on the exact context. Okay, so again, just to repeat, an Eulerian trail is a walk in a graph that includes each edge exactly once. Okay, so that is what an Eulerian trail is, and that's the thing we're going to be interested in for now. It's an Eulerian circuit if it also returns to the vertex it started at. Okay. So I want to try to convince you how we should think about this. And so I want to try just some random way of doing this. So I'm going to start here, come over here, down here, up here. Well, that was bad because then I got stuck. So maybe I'm going to have started down here instead, going up there. And so maybe I'll work backwards. And so say, okay, now I've started here, gone there, and then I'm going up there and there and there. And I can try and sort of figure out, okay, where am I starting and where am I stopping, and all that sort of business. So kind of go on. So I can go back to starting to here, go to here, 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 here. So I want to look at this particular vertex, and I want to look at each edge that's connected to it. And each of those edges either corresponds to an edge that I used to leave this vertex, or an edge that I used to enter this vertex. And so I'm going to label those out edges, the edges that I used to leave, and in edges, the edges that I used to come in. And I want to notice for this particular vertex, and in this particular arrangement, that I have two out edges and one in edge. And if I figure out what that means I left this vertex one more time than I came into the vertex. And if I think about it, what does that mean? That means I had to have started here. Okay. And so you can actually tell a lot about what happened at a particular vertex based on how many out edges there are and how many in edges there are. Okay. So I'm going to label here three kinds of vertices on an Eulerian trail. And so the first kind is that kind. So the starting vertex, it has number of out edges is one more than the number of in edges. Okay, I leave the vertex one more time than I come in. There's also the ending vertex. And that will have the opposite, right? At the ending vertex, at the very end, I'm going to enter it and not leave. And so this will have the number of in edges is equal to the number of out edges plus 1. Okay. And every other place, I have to enter the same number of times as I leave. Okay, and I up here labeled that this is true for any Eulerian trail. This is actually true for any trail at all, that everything breaks down into one of these three cases. The only thing that's special on an Eulerian trail is that then every edge is used, so every edge is an out edge or an in edge. Now I want to make an observation here that on an Eulerian trail, this means the total number of edges that touch that is of necessity odd. Why is it that this degree is odd? It's because the number of out edges plus the number of in edges is going to be the total degree, but the number of out edges plus the number of in edges, because of this equality, is the number of in edges plus the number of in edges plus 1, which is twice the number of in edges plus 1, which is exactly saying that this number is odd. Okay. Ditto here. This degree is also odd. But finally, on these other vertices where the number of in edges is equal to the number of out edges, this means that this degree is even. Okay, so this is basically a proposition that lets me figure out, okay, what do starting vertices look like? What do ending vertices look like? And what do other vertices look like? And so starting vertices and ending vertices, they both have odd degree, whereas other vertices of necessity have even degree. Okay. So I want to go back. I want to redraw the graph of the bridges of Königsberg. And so it looked like this. Okay, and I want to count the degree here. So this is degree 3. This up here is degree 3. This is degree 3. And this is degree 5. Okay, so if you believed what I wrote here, then this vertex, because its degree is 3, it has to be either the starting or ending vertex of an Eulerian trail. This one also must be the starting or ending vertex of an Eulerian trail. And same with this one, and same with this one. So, by the above, every vertex in this graph must be a starting or ending vertex of some hypothetical Eulerian trail. But if you think about it, that's a problem, because I only get one starting vertex and one ending vertex. Okay. And so this gives me a proof by contradiction that there is no Eulerian trail here. Which I'm just going to abbreviate as ET in the Königsberg graph. And so this answers the question in the negative about whether it's possible to go across every bridge in the bridges of Königsberg exactly once. And let me frame all of that in a proposition. Namely, my proposition here is going to say that a necessary condition for the existence of an Eulerian trail in a graph is that it have either exactly 2 vertices of odd degree or no vertices of odd degree. Okay, so what this proposition says is that a necessary condition for the existence of either an Eulerian trail or an Eulerian circuit. Remember, an Eulerian circuit is just an Eulerian trail that starts and ends at the same place, which, if you want to think about it, really means there is no start and end, because you could just go around the loop forever and ever and ever, is that the graph has either exactly two vertices of odd degree, in which case there's a distinct start and end point, namely those two vertices of odd degree, or exactly zero, in which case then potentially there's an Eulerian circuit. Any other number of vertices of odd degree, and we immediately know that there is no Eulerian trail / Eulerian circuit. Remember, what does necessary condition mean? It means that if this condition isn't fulfilled, there definitely isn't one. Okay, so let's just draw a kind of random looking graph. Okay, and we could ask ourselves, if I take this kind of random looking graph, can there possibly be an Eulerian trail in this kind of random looking graph, or an Eulerian cycle? And the answer is no, because this graph has 4 vertices of odd degree. So all 4 of these vertices would have to have all 4 of these vertices would have to be either the start or end point, and I don't get that many start / end points. Okay. What about this graph? Okay, so this graph is on 6 vertices. I put a vertex here in the middle. Does this have an Eulerian trail in it? I'll note this picture is something that often shows up in children's puzzle books under the guise of, hey, here's a picture, can I draw this picture without picking up my pencil? And that's in fact exactly the same question as whether there's an Eulerian trail in this graph or not. So we know now the thing we're supposed to zero in on right away is, hey, where are the vertices of odd degree? This vertex has degree 2, degree 4, degree 4, degree 4, degree 3, and degree 3. Okay. So that tells me if I'm going to find one, I had better find one that starts and ends at these 2 points. Note the starting and ending point are really symmetric, because if I have a trail that starts here and ends here, that's Eulerian, then I could go on that exact trail backwards, and then it would start here and end here instead. Okay, but let's try this. So, namely, let's go from start here. So here's my start. Then we'll go here, 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 7, 8, 9, 10. Okay. And so I've outlined for you, start here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that gives us our Eulerian trail. So in fact, here the answer is yes, there is an Eulerian trail in this graph. Here the answer was no, there's not. And I'll notice this proposition and the ideas behind it didn't just fail to contradict that this had an Eulerian trail. It at least gave me a hint that, hey, I want to really start at one of these spots. And in this case, then we ended here. Okay. And notice we sort of psychically knew before we even started that when we started here, that we were going to end here if we found one. Okay, I want to note one more necessary condition. Because a necessary condition for a graph with no isolated vertices to have an Eulerian trail is that it's connected. Okay, by the way, before I justify why this is true, what's an isolated vertex? An isolated vertex is a vertex of degree 0. So if you look at this example we just did where there were 6 vertices, if I put a vertex up here, and a vertex up here, and one over here, and one over here, there's still an Eulerian trail through this graph, the same one, because being an Eulerian trail only means something about visiting the edges. And so if your vertex is there and it has no edges connected to it, it has no bearing at all on what happens. So we might as well just throw those away before we even start, and then we can look at what's left. But what does this say? It has to be connected. Why does the graph have to be connected? And what we should remember does connected mean? Connected means that any pair of vertices, it's possible to walk between them. Well, once there's no isolated vertices, then our trail here is a walk that starts here and ends here, and of necessity visits every vertex, because it has to visit every edge. And now that we've assumed there's no isolated vertices, that means it visits every vertex, because you can't visit every edge without visiting every vertex, once there's no isolated vertices again. And so that gives us a walk that, among other things, starts here, visits every vertex at least once, and ends here. And so that means any 2 vertices you pick, be it that one and that one, or that one and that one, or whatever, whichever 2 of them, you can just use the trail that you have to connect, to write down a walk that goes from one to the other. Now, if you think about what this is really saying, this is saying something that's kind of ridiculous, which is that if you make this graph with these 10 vertices, there's definitely no way to write down an Eulerian trail through this graph, because I can't even get from this edge to this edge over here, from this vertex to this vertex. And even if I go ahead and fix this so that all of the vertices have even edge, or have even degree, which I realize I did not, it's not going to help me. I exactly the opposite of fixed that. But even if I somehow connect all of these things up so that they have even degree, it's not going to matter. There's no way I could possibly visit every vertex, because again, I just can't get from this piece to this piece. Okay, so this is really the more obvious necessary condition. Okay, but it is a big theorem of Euler, and so this is also sometimes called Euler's theorem. Again, there are a lot of Euler's theorems. That these 2 necessary conditions, that is, that the graph have either 0 or 2 vertices of odd degree, and that the graph be connected if it has no isolated vertices, those 2 are also sufficient for there to be an Eulerian trail / cycle. Okay. And if you think about it, what this tells you is that if you have a graph with no isolated vertices, and the graph is connected, and it has exactly 2 vertices of odd degree, then there is an Eulerian trail that starts at one of those vertices and ends at the other. Or, if you have a connected graph where every vertex has even degree, then there's an Eulerian circuit in the graph. That is, there is one of these walks that visits every edge exactly once. So this makes it very, very easy to look at a graph and immediately tell you whether the graph has an Eulerian circuit / an Eulerian trail or not. Okay. One more question before we end this video. And in the next video, I'll explain why this is true, by the way. But one more question, if we think about this. What if a vertex has exactly... Or sorry, one more question. What if a vertex has exactly one vertex of odd degree? Okay. So we said what happens if a graph has exactly 0 vertices of odd degree or exactly 2 vertices of odd degree. But what if there's exactly one vertex of odd degree? Then what happens? Well, as it would happen, this is impossible. Not it's impossible for there to be an Eulerian trail. It's just literally impossible to make a graph with exactly one vertex of odd degree. Why? Because of the handshaking lemma that says if you sum the degrees of the vertices, then you always get twice the number of edges. In particular, if you sum the degree of every vertex, you get an even number. And so therefore, you can't sum exactly one odd number and a bunch of even numbers and get an even number. So that's not possible. Okay. So these are basically the small possibilities. Either there's 0 vertices of odd degree, or the next smallest is there's 2. And then the next smallest after that is there's 4, and so on. Okay, we'll wrap up there for this episode. Again, next episode, we'll go through and we'll prove this theorem. Namely, we'll prove that if you know a graph has either 0 or 2 vertices of odd degree, and it's connected, then there is an Eulerian trail through it. But until next time, be well.